Somewhere out beyond the edge of everything we call home, a machine older than most of the people reading this is of space so far away that even light, the fastest thing in the entire universe, needs a full day just to reach it. But here's the part nobody is talking about. In the last few years, this machine has started recording something in the empty dark that don't realize is that Voyager 1 finished its official job decades ago. Everything it has done since then is bonus footage in the story of human exploration, except the stakes have only gotten higher, not lower. Somewhere along the way, this 5-year mission quietly turned into the most important long-formed analysis of the mission's own telemetry. The region just outside our solar system is not the flat, dead vacuum it was long assumed to be. Voyager 1's plasma wave instrument picked up something that scientists can only describe as a persistent, steady hum, a faint vibration moving through the charged particles that drift between the stars. This was not random noise, it was structured. It behaved like a signal moving through a medium, the same way sound moves through air. Except this air was interstellar plasma, thinner than anything we can recreate in a lab, sitting in a region of space where temperatures and pressures should make consistent, measurable activity almost impossible. Read that again. A spacecraft built in the 1970s, using instruments with a fraction of the sensitivity of modern technology, detected a persistent vibration moving through supposedly empty space between star systems. That finding alone forced researchers to rewrite their understanding of what nothing actually means in interstellar space, somewhere past the edge of everything humanity has ever mapped. A machine older than the internet, older than cell phones, older than most of the people currently. Keeping it alive sent a signal back to Earth that took 23.5 hours to arrive. 23.5 hours for a whisper of electricity to cross 15 billion miles of nothing. And when that signal finally landed in a control room in Pasadena, the engineers reading it did not see triumph. They saw a warning. Something on board had gone wrong, unexpectedly, silently. Nobody had seen it coming. This is the story of what happened next, and why it matters more than almost anyone is talking about. To understand why that warning mattered, you have to go back to a decision nobody questioned for almost 50 years. In 1977, NASA launched 2 machines into space with a jump and may not touch again for a generation, if ever. There's a symbolic marker sitting on the calendar that makes all of this even more charged. In November 2026, Voyager 1 is projected to cross a milestone known as 1 light day from Earth, a distance of approximately 25.9 billion kilometers. The exact distance light itself travels in 24 hours. It will be, in some ways, a strange kind of anniversary, a number that sounds abstract until you actually sit with it. A signal leaving Earth right now, traveling at the fastest possible speed anything in this universe can travel, will need a full day just to catch up to where Voyager 1 will be. And engineers are trying to keep that spacecraft alive, functioning, still listening, still speaking as it crosses that threshold, all while gambling on an unproven power-saving maneuver that could either extend its life for years or accidentally cut it short before it ever reaches that symbolic distance at all. So where does that leave us right now in the middle of this unresolved story? As of the most recent confirmed updates, the Big Bang procedure was scheduled for testing on Voyager 2 through May and June of 2026, with a decision on whether to attempt the same maneuver on Voyager 1 expected no earlier than July. Whether that test succeeded, whether Voyager 1 will actually undergo its own version of the maneuver, and whether the sacrificed LECP instrument will ever hum back to life 15 billion miles from home remains genuinely uncertain, still unfolding as engineers on Earth wait out day-long delays between every single command and every single response. Nobody, not the mission managers, not the instrument scientists, not anyone watching this unfold from the outside, can say with certainty how this ends. The craft's power levels dropped unexpectedly, not on schedule, not part of the plan, a deviation out there in the freezing dark. 15 billion. Miles from anyone who could physically intervene. Think about what that means for a moment. There is no repair crew. There is no backup system waiting on standby. There's a team of engineers on Earth staring at telemetry data that is already 23 hours old by the time they receive it, trying to diagnose a problem on a machine they cannot touch, cannot see, and cannot reach, in less than a full day of radio travel in either direction. Whatever happened during that roll maneuver, the ripple effects were immediate and impossible to ignore. The response came fast, and it was brutal in its simplicity. On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent a command across the solar system, across the heliosphere, out into true interstellar space, instructing Voyager 1 to shut down its low-energy charged particles instrument, known as the LECP. This was not a minor sensor. This was one of the defining scientific tools of the entire mission, an instrument that had operated almost without interruption since the day Voyager 1 left Earth in 1977. It was the LECP that helped scientists first confirm Voyager had crossed the invisible boundary, out of our solar system and into the true space between stars. According to the instrument's own principal investigator, Matt Hill, working out of Johns Hopkins Applied Physics Laboratory, this was the tool that let scientists sense the changes in the region around the spacecraft, the very changes that told humanity the exact moment we had left home behind. And now, in 2026, it had to be sacrificed. Not because it broke, because there simply was not enough electricity left in the machine to keep it running. Sit with that for a second. Out of the 10 scientific instruments Voyager 1 originally carried into space, only 2 remain active today. 2, a magnetometer and a plasma wave subsystem. That's it. That is the entire scientific output of humanity's most There are 2 trillion galaxies in the observable universe. 2 trillion. Each one containing hundreds of billions of stars. Many of those stars with planets. Many of those planets sitting in the exact zone where liquid water can exist, where chemistry can organize itself into something living, where life, by every statistical model we have, should have emerged, evolved, and reached intelligence long before humans figured out how to build fire. The math is overwhelming, the probability is staggering, and yet, in 70 years of scanning the sky with every instrument we have, in thousands of hours of radio telescope listening, in signal analysis that spans every detectable frequency, nothing, not a whisper, not a pattern, not a single confirmed transmission from a single other mind in the entire observable universe. Silence, total, complete, universe-wide silence. That is the Fermi paradox. And when scientists asked Grok, Elon Musk's AI, one of the most powerful language models ever built, to solve it, the answer it gave was not what anyone expected. It was not reassuring. It was not optimistic. It was the kind of answer that makes physicists go quiet. This is that story. To understand why Grok's answer landed the way it did, you need to understand exactly how strange the silence is. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Intelligent life on Earth, the kind that builds tools, develop, PS language, eventually constructs radio telescopes and spacecraft, has existed for perhaps 200,000 years. That is 200,000 years against a 13.8 billion year backdrop. A civilization that got started just 1 billion years before us, 1 billion years earlier, in a universe that had been running for over 12 billion years at that point, would be so far ahead of us technologically that the gap is genuinely incomprehensible. Not slightly more advanced, not a few generations ahead. They would be to us what we are to bacteria, maybe further. Their technology would be indistinguishable from what we would call magic or physics we haven't discovered yet, or reality itself behaving differently. A civilization 1 billion years old with 1 billion years of scientific progress, with 1 billion on years of resource accumulation and expansion, that civilization should be visible across the galaxy, should be impossible to miss, should have colonized, transformed, or at minimum left unmistakable traces across thousands of star systems. And yet, nothing. In 1950, the physicist Enrico Fermi sat at lunch with colleagues at Los Alamos and asked a question so simple it seemed almost naive. Where is everybody? That question became the Fermi paradox. And in the 75 years since, some of the greatest scientific minds on Earth have tried to answer it. They proposed the Drake equation, a mathematical framework for estimating how many communicating civilizations should exist in the Milky Way alone. When you run the numbers conservatively, the answer comes back in the hundreds. When you run them optimistically, the answer comes back in the millions. Either way, the answer is not 0, and yet the signal count remains exactly 0. Every answer that has been proposed, every theory, every hypothesis, every framework, the why, all collapse into the same uncomfortable territory. Either life is extraordinarily rarer than we think, or something is happening to civilizations before they can reach us. Or, and this is the answer Grok leaned into hardest, they are already aware of us, and they have made a deliberate choice. A team of researchers, led by Dr. Priya Chandra and Dr. Julian Marsh at MIT, designed a structured research protocol to probe Grok's reasoning on first contact scenarios and the Fermi paradox. They weren't looking for summaries of existing theories. They wanted Grok to reason through the problem using only physics, game theory, and information theory as constraints, stripping away human cultural assumptions, human optimism, human desire for a friendly universe. The early sessions produced what you'd expect: organized summaries of the Drake equation, the Great Filter Hypothesis, the zoo theory, competent, structured, nothing surprising. B. OT, as the team pushed deeper, asking Grok to construct original models of first contact under realistic physical and game theoretic constraints, the responses shifted. And one response in particular stopped the researchers cold. Grok's core proposition was this: any civilization capable of detecting humanity has almost certainly known about us for a very long time. Not years, not decades, potentially millions of years. The reasoning behind that statement is where things get interesting. Humanity has been In broadcasting electromagnetic radiation, radio waves, television signals, radar pulses, the electromagnetic fingerprint of an industrial civilization, since roughly the 1880s. Those signals travel outward from Earth at the speed of light and have now reached a sphere approximately 140 light years across. Within that sphere, based on current exoplanet surveys, there are thousands of star systems, many with planets, some almost certainly with conditions and suites, for life. Any civilization within that sphere with radio astronomy, equivalent to what humanity had in the 1960s, would have detected our signals already. And a civilization that developed radio astronomy before us, which, given the age of the universe, could mean a civil decade, past the point where every engineer who built them assumed they would already be dead metal drifting in silence. What most people are not seeing is that this survival was never guaranteed, and it was never permanent. Every single day since 1977, a process has been quietly ticking away inside both spacecraft, a process nobody can stop, slow down, or repair from 25 billion kilometers away. Each Voyager runs on something called a radioisotope thermoelectric generator, essentially a nuclear battery that converts the heat of decaying plutonium into electricity. There's no sunlight to rely on out there. At Voyager's distance, our sun is just another star in the sky, too. Faint and too far to power anything. So the plutonium has been doing all the work alone for 49 years. And plutonium, like everything else in the universe, obeys a law nobody can negotiate with. It decays. Every year, both spacecraft lose roughly 4 watts of power. Read that again. 4 watts. Less than a household light bulb. That is the entire margin standing between still exploring and gone forever. For most of Voyager's life, that slow bleed of power was manageable. Engineers could shut off an instrument here, heater there, and buy themselves another year, then another, and then another. It became almost routine. In September 2024, Voyager 2's plasma science instrument went dark. In February 2025, there are 2 trillion galaxies in the observable universe. 2 trillion. Each one containing hundreds of billions of stars. Many of those stars with planets. Many of those planets sitting in the exact zone where liquid water can exist, where chemistry can organize itself into something living, where life, by every statistical model we have, should have emerged, evolved, and reached intelligence long before humans figured out how to build fire. The math is overwhelming, the probability is staggering, and yet, in 70 years of scanning the sky with every instrument we have, in thousands of hours of radio telescope listening, in signal analysis that spans every detectable frequency, nothing, not a whisper, not a pattern, not a single confirmed transmission from a single other mind in the entire observable universe. Silence, total, complete, universe-wide silence. That is the Fermi paradox. And when scientists asked Grok, Elon Musk's AI, one of the most powerful language models ever built, to solve it, the answer it gave was not what anyone expected. It was not reassuring. It was not optimistic. It was the kind of answer that makes physicists go quiet. This is that story. To understand specific locations in the sky with a precise eye, on that demands intentionality. And that intentionality demands knowledge. Knowledge of a kind and a depth that the conventional story of ancient Egypt does not fully explain. Grok then turned to the Sphinx. The Great Sphinx sits on the Giza Plateau, carved directly from the living bedrock, facing due east toward the rising sun. On its body, particularly on the vertical walls of the enclosure in which it sits, there are patterns of erosion, deep, rounded channels carved by flowing water. Not by wind, not by sand, by water. Significant quantities of water over an extended period of time. The problem with this observation, which was first made, credibly by geologist Robert Schoch in the early 1990s, is that the Giza Plateau has not received that kind of rainfall since approximately 7,000 to 10,000 BC. The conventional dating of the Sphinx places its construction around 2500 BC, contemporary with the pyramids. But if the erosion patterns on the Sphinx enclosure were caused by rainfall, then the Sphinx must have been built during a period when the Sahara region received heavy and sustained rainfall. And that pushes the construction date back not by a few centuries, but by thousands of years. When Grok analyzed the geological data from Schoch's research, from subsequent studies by other geologists, and from seismic surveys of the bedrock beneath the plateau, it identified this as one of the most underexamined inconsistencies in mainstream Egyptology. The mainstream response to Schoch's water erosion hypothesis has largely been dismissal. But dismissal is not the same as disproof, and the geological evidence, when examined without institutional bias, remains stubbornly intact. What makes Grok's analysis different from the kind of speculation that floods the internet about ancient mysteries is that it does not leap to conclusions. It maps the evidence. It lays out what is known, what is contested, and what is currently unexplained, and then it models the probabilities. Somewhere out beyond the edge of everything we call home, A machine older than most of the people reading this is of space so far away that even light, the fastest thing in the entire universe, needs a full day just to reach it. But here's the part nobody is talking about. In the last few years, this machine has started recording something in the empty dark that don't realize is that Voyager 1 finished its official job decades ago. Everything it has done since then is bonus footage in the story of human exploration, except the stakes have only gotten higher, not lower. Somewhere along the way, this 5-year mission quietly turned into the most important long-formed analysis of the mission's own telemetry. The region just outside our solar system is not the flat, dead vacuum it was long assumed to be. Voyager 1's plasma wave instrument picked up something that scientists can only describe as a persistent, steady hum, a faint vibration moving through the charged particles that drift between the stars. This was not random noise. It was structured. It behaved like a